This video is part of CAE Associates Ansys e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of Ansys courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
My name is Mike Huron, and welcome to the latest in CAE Associates e-learning series. Today we're going to be talking about CFD meshing with Ansys Workbench. So we'll be covering some topics that are particularly relevant for you CFD users out there, and we'll talk about the different mesh methods. And on our agenda, in addition to the mesh methods, is how do we get an efficient mesh? So what is the most efficient way to go about using Ansys Workbench when we're generating a mesh for CFD? And after that, I'll do a live demonstration of the meshing process on a real part. Now, one administrative note before we get started: we are offering one PE credit for those of you that are interested in. We do require that you participate in the polls and also the follow-on survey, so make sure you do that if you're interested in the PE credits, and then we'll follow up with you afterwards. Okay, let's get started here. So the first thing that we want to talk about are the different Ansys Workbench mesh methods. So we have a number of different mesh methods, and they can be divided into two basic categories. So we have the hexahedral methods, and these include methods like sweep, multi-zone, and more exotic methods like hex dominant and cut cell meshing. Now we're going to concentrate on sweep and multi-zone today, but the point to understand here is what type of elements they're going to create, and also some characteristics of these methods. So in general, hex methods will require more effort on the user end because we'll have to satisfy certain geometric requirements, but the end product, or the mesh that we create using these methods, is oftentimes much more efficient than the alternative. Now the second category is the tetrahedral methods. So these are going to create tetrahedral cells, and we have two different algorithms in Workbench meshing that we can use in order to generate a tetrahedral mesh. That's the patch conforming method and also the patch independent method. And we'll talk about the differences and the subtle nuances of each in just a moment. The key with TET methods is that it's much easier to fill an arbitrary volume with TET cells than it is with hexahedral cells. So there's much less user interaction on the front end, but we may not always get the most efficient mesh for our analysis. So let's take a closer look at these methods. The first one is the sweep mesh method. Now the sweep has very strict topology requirements in that we require a consistent source and target face. So we need to have a single source and a single target face that have the same topology, so the same number of vertices per face. And we also have to have a smooth path from the source to the target. So if we look at our example part that we have shown on this slide here, we have an extruded topology. So we have one face that has two holes in it, and that gets extruded along a path. And this fits the requirement for a sweepable body. We have a source face that you can see on the right-hand side that has 4 vertices, and it has 6 edges. And we have the same exact face on the opposite end of the body, so we can sweep from that source to the target along a smooth path. Now the sweep mesh method is the default approach for Workbench meshing. So Workbench will go through and try to detect whether you have any sweepable bodies, and we'll go ahead and put a brick mesh or a hex mesh on those bodies. If it can't do that, it'll use a tetrahedral mesh method. Now, typically what Workbench meshing will do is automatically detect whether if a body is sweepable and what the source and target faces are, But in certain instances, for instance, if there are more than one possible sweep direction or you want to use inflation layers, you may want to specify manually what the source space is going to be. And we can do that in the details pane. So if we look at the section of the details pane for the sweep method, we can see we have source and target selection definition. By default, that'll be set to automatic, but we can also specify that to be a manual source where we specifically tell Ansys Workbench which face we want to use as the source. So we have a lot of control over this mesh method. However, due to its strict topology requirements, we may not always have our flow domain in such a state that we can automatically just mesh it with the sweep mesh method. So we may need to do some geometry manipulation or maybe use different methods. But the nice part about the sweep mesh method is that we have great control over the element distribution. So not only can we control on the source and target faces what the mesh looks like, but we can also control how the mesh propagates between the two. And we can do that using the sweep bias. So this allows us to cluster elements in various patterns. Either, let's say we want to have smaller elements in the middle of the sweep, or maybe we want smaller elements on one side of the sweep. We can do that using the sweep bias type. So from the drop-down menu in the details pane, we can set a sweep bias, and we can set, in addition to that, a sweep bias factor. And what the bias factor indicates is what the ratio of the largest element to the smallest element is going to be. So you can see in this instance, we've set a sweep bias so that on the ends of the sweep, we have smaller elements than in the middle. And the bias factor set to 2 means that the middle elements will be twice as big as the elements on the end. So the key advantage of the sweep mesh method is that it efficiently fills a volume with bricks and also gives us a great level of control over what those elements will look like. An additional method that is used to create hex elements is the multi-zone method. And this is courtesy of the ISOM advanced meshing tools. And what this does is tries to internally segment bodies into topologically consistent pieces. So it'll try to do an automatic geometry decomposition so that it can create brick elements using a sweep method. So if we see our example part here, on the left, just the geometry, we don't have a single source and target face, but we do see a lot of the prismatic features that we can maybe decompose this body into a sweepable body, into sweepable subdivisions. Now, multi-zone is not foolproof, but it will try to do that for you and do that geometry decomposition. And in this case, it's pretty successful. We're able to generate a brick mesh. Certainly on these inlet pipes are entirely bricks. In the core region, we do get some tetrahedral elements mixed in, but for the most part, we get an all-brick mesh. So a very powerful method, but certainly not foolproof. The only guaranteed way to get an all-hex mesh is to do the slicing and dicing method, which I'll demonstrate a little later on. Now in CFD, for CFD flow domains, the reality is that for the most part, we're not always going to have domains that are able to be decomposed into sweepable sections. Now, in that case, we're going to have to use tetrahedral mesh methods, and this is a very common solution to the complicated geometry that we see. Now, in Workbench, we have two different algorithms for tetrahedral meshing. The first is the patch conforming. The patch conforming basically builds our mesh from the bottom up. So we mesh our edges first, then we mesh the faces, and finally we fill in the rest of the volume with tetrahedral elements. So in this case, the mesh has to conform to all the boundaries of our part. So whether we have very tiny edges, we have small faces, the patch conforming algorithm has to respect all of those geometric entities because of the nature in which the mesh is built. So we like to say this method or this algorithm is good for what we call clean geometry. So geometry that has been cleaned up or doesn't have any small features or difficult faces to work with, the patch conforming method will be very effective. Now, on the other hand, we have the patch independent algorithm, and this works just the opposite. This builds a volume mesh first, then projects that to the faces, and finally to the edges of our part, or of our flow domain. And this is very, very useful in that it's not necessarily required to conform to the boundaries of the faces. Sure, it will certainly try to project to those, to the faces of our part, but if we have small faces or fine edges, that will create a very fine mesh. The patch-independent mesher or algorithm has the ability to walk over those features. And let's take a look at an example of that. If we take a look at this, this geometry we have here, where we have some small faces and small edges relative to the overall geometry size, we can see that the patch-conforming mesh has to adhere to all of those small features. So we get some small sliver elements. We get a rather refined mesh in the regions of the fillets, and certainly in the corner on the bottom left, we get some very fine elements. And the resulting mesh, even though it's coarse, is around 28,000 elements for this body. Now, on the other hand, the patch-independent mesher is able to walk right over those features, so it doesn't have to respect those faces. We see for this mesh, we get an equally valid approximation to this body, and we have a mesh of only 11,500 elements. So two different approaches that are useful in different circumstances based on the features of your geometry. Okay, at this point, what I'd like to do is take a quick break, and we're going to do our first poll. So if we return here, let me open up this poll, and what we'd like to get your input on is what percentage of your time do you spend meshing during the analysis process? So let's open up this poll. We'll take about a minute to get everyone's answers, and then we'll continue on talking about efficient CFD meshing. And as we can see, we get quite a bit of people spending spending quite a bit of time in the meshing process, and that's pretty typical. The meshing procedure can be time-consuming and is a very important part of our overall process, so we want to make sure we get that right. And it's not always going to be our first time through is going to produce the perfect mesh, so we may have to iterate on that a couple times. Okay, let's go back to our PowerPoint here, and now what we're going to talk about is how do I generate an efficient mesh. So I have all these mesh methods at my disposal, and what's the most efficient way to generate a mesh for CFD? Well, in order to decide what that most efficient method is, let's think about how our elements are generated. Basically, we have a few basic shapes. We have on one extreme the hexahedral elements, which we talked about generating using sweep and multi-zone methods. On the other extreme, we have tet methods, which we talked about generating using patch-conforming and patch-independent. And in between, we have wedges and pyramids that we use to connect the two. Now, hexahedron elements can generally fill a volume much more efficiently than other shapes. So we can take, let's say, 5 to 6 tetrahedrons just geometrically to fill one hex with the same resolution of our solution. So if we have 5 to 6 times fewer elements, we'll have 5 to 6 times faster solution times. So certainly using brick elements can be very advantageous in getting our solution times and our mesh sizes down. In addition, hex elements or hex meshes are generally much more controllable, much more uniform, and we have a great deal more control over how we distribute our elements. So, we have a lot of advantage there in being able to space our elements and group them more tightly in regions where we need them, and then maybe we can make our mesh a little coarser in regions that don't play as big of a role. And they can also be more accurate when aligned with the flow direction. Now, this is not always possible, certainly if we have a complicated flow field, but it is important to note. So what do I need to do in order to get a hex mesh? Well, the rule of thumb here is that hex meshes are always going to take more man time than tet meshes. That's certainly can be borne out by experience. And the reason is, typically, to create a hex mesh, we need to take a number of steps. When we're creating a tet mesh, all we need to do is specify the method and tell the meshing algorithm to go do its work. For a hex mesh, on the other hand, we may need to do some geometry decomposition. We may need to clean up our geometry so that it fits our topological requirements. And the basic approach is to do first some slicing and dicing. So we want to create or split up our flow domain geometry to create 6 faced volumes. So each are going to have a certain number of boundary curves. We're going to have a source and a target that are topologically consistent, and a way to sweep along, a smooth path to sweep along from the source to the target. So once we have our geometry figured out, we're going to create a 2D mesh of quadrilaterals and either sweep or extrude them to create 3D hexes. And now that can be revolving about an axis, that can be sweeping along a direction, and all of these processes are grouped into the sweep mesh method. So that's not something you have to do manually. That's something Workbench will do for you using the sweep mesh method. Additionally, we can also use advanced methods like the multi-zone method, but the only foolproof way of creating a brick mesh or a hex mesh is to do the manual slicing and dicing. So you may say, why would I want to go through all that effort in order to create a hex mesh? I know we can create a more efficient or a smaller mesh with the same resolution, but is it really going to make all that difference? Well, let's take a look at an example. If we look at the part below, I think we had seen the multi-zone applied to this earlier, but if we take a look at its original geometry, we can see that in its present form, we won't be able to create an all hex mesh. We don't have a consistent source and target face. However, with a little bit of effort by the user, we can do some geometry manipulation and create entirely sweepable bodies. So let's take a look at the results here. By creating a few slices in Design Modeler, what I've been able to do is create a number of bodies. It looks like I have 13 bodies, I believe. I've formed them into a part, so I have a continuous mesh, and I have all sweepable bodies. Now I've generated the mesh with the constraints that I want to accurately capture the curvature of the inlet pipes, and I want to have 5 inflation layers along all the walls. The result of this, in addition to the mesh density in the mixing region, is that I have a little over 125,000 elements. So really not too bad, a pretty efficient job at creating the mesh here. Now, if I had done no geometry work at all, if I hadn't done any slicing and I just said, hey, let me give this to the tet mesher and I'll see what it comes up with, well, what I'd end up with the same mesh resolution is almost 4 times as big of a mesh. So almost 500,000 elements for the same mesh resolution. Now, there was very little effort on my end to create this mesh, but the solution is going to take 4 times longer to generate. So if it takes, if the solution is complicated, or maybe I have to run a number of different iterations on the boundary conditions, the savings in the mesh are going to grant me a great deal of flexibility when it comes to the solution time. So I'll get a much quicker answer if I put in a little bit of effort on the front end. So certainly, this appears to be worth it. And now that I've convinced everyone that a brick mesh is what you want to do, how do I go about and do that in Workbench? Well, let's recall that we had several mesh methods that create hex elements. We have the sweep and the multi-zone, which we talked about. And we also have a hex-dominant method that we don't suggest using for CFD analysis, but can be useful for structural analyses. Now, each of these methods has different geometry requirements, so it's important to understand how they behave and what they are. But in a lot of instances, what's going to happen is you're not going to be able to get a mesh that's entirely hex elements. We're going to have complicated regions that we're just simply not going to be able to decompose into sweepable parts. And what we can do is use the selective meshing feature of Workbench meshing in order to create as many hexes as possible and then fill the remainder with tets. What selective meshing allows us to do is use specific methods in a multi-body part. We can combine any number of different methods, and we can mesh them in any order that we see fit. So in this example here, which I'm going to walk through in just a minute, we have a sweep method, we have a multi-zone method, and we have a patch conforming method, all in one multi-body part. And the mesh is continuous, And we've used selective meshing to dictate the order in which the mesh gets generated, which is a really important feature. So we can choose that this body on the left gets generated first, then this body on the right, and finally the body in the middle. And the important part about that is we can use the existing mesh to influence the downstream mesh. So if we generate the mesh here first, we have hex elements here. We can use those hex elements on the boundary to influence how the mesh gets generated in the adjacent region. So it's a really powerful method for controlling your mesh. Now, in order to record the operations that we do, we can use the worksheet. And I'll show you an example of this, but basically what we're going to be able to do is record the order in which those bodies get generated. So let's take a quick break right here, and we'll do our second poll. And once we're done with that poll, I'll go into our live demonstration. But what we'd like to get some feedback on here is what your biggest bottleneck is when you're going through the meshing process. So let's open that up for just a minute and get everybody's feedback, and then we'll keep going. There we go. Looks like everybody's finished up. So it looks like one of the biggest bottlenecks for everybody is being unfamiliar with the mesh controls. And hopefully through our e-learning series and additionally through our training, we can bring everyone up to speed, because certainly those are the most important aspects of generating a mesh. Is we want to control on a fine level what our mesh looks like and how we can control the element distribution. So be sure to stay tuned to our different e-learning series and training opportunities as well. Okay, so let's take a look at an example of how we go through this efficient meshing method. And what we're going to do is take a look at, if we open Design Modeler, we'll take a look at a part that we had used in our previous CFD or e-learning series or e-learning session, where we extracted the flow domain. So for those of you who didn't attend or maybe have just forgotten, what we had here was a ball valve section. So what we have is a rather complicated internal geometry. If we take a look at the solid part now, if we see from either end, we have some complicated features on the interior. And what we went ahead and did previously was extract the flow domain here, if I just suppress the solid bodies. And you can see I have some long cylindrical sections, and then the ball valve section in the middle, which has some more complicated features. So if by first pass what I do is just open up Workbench meshing and assign a tetrahedral method, in this case I use the patch conforming method, to just go ahead and tackle this geometry in a brute force method. And what you can see is the resulting mesh. It looks great. I mean, I have a pretty uniform mesh distribution. I have a very fine mesh in the region of these fillets. The mesh is getting refined due to the curvature, and I have what appears to be a lot of tet elements. If I take a look in the details pane under my statistics, I have over 700,000 elements just using this brute force mesh method. So I think I can do a little better than that if I take the time to do some geometry manipulation. So let's go back and go to Design Modeler and take a look at what we have here. So my goal is to somehow split this body up or partition this body so that I can sweep mesh certain parts of it. So what I think I can do is I can maybe just separate this part out here and this cylindrical part out here, and I think that they'll be sweepable. So in order to partition them, what I'm going to do is use the slice operation. So if I go ahead and insert slice into the outline tree, one of the very useful options here is to slice by edge loop. So I have these conveniently defined edges based on how I built my flow domain. And if I use them to slice, I'm going to target just this body here. Let me go ahead and generate that. And for some reason this gets put into that part. Not sure where that happened. And what I can see here is now I have three different partitions. So I have two cylindrical bodies, and those should be perfectly sweepable. I should be able to get a brick mesh on them, no problem. But I still have this complicated region, but at least I've limited where I need to have tet elements to the complicated region. Now, as it stands now, this part will not be meshed with a continuous mesh across these boundaries. The reason is I have 3 distinct bodies. If I want the mesh to be continuous throughout the body, what I need to do is form them into a multi-body part. So if I select all 3 of these, I right-click to open up my context menu, and I say Form New Part. Well, you can see in the outline tree, now I have the flow domain formed into a part with my 3 bodies. And this will guarantee that I have a continuous mesh across the interfaces here. Now, one additional step I want to take, just to limit the mesh density, is to try to remove some of these fillets in this region. Maybe for my first pass analysis, I don't need them. I just want to get a general idea of what the pressure drop is, and I don't think they're going to play that big of a role. So what I'll do is select 2 of these faces, and then I'm going to use the Flood Blends feature in order to extend that selection out along. Now, I want to limit that to just the fillets on the outside radius. So let me just quickly unselect these faces here, so that when I go ahead and use my face delete operation, I won't have I will only capture the fillets on the outer radius, and so that'll rid me of those details. But maybe I want to keep the vertical fillets. So let me go to the Create menu, do a face delete, and if we take a look at what this is going to do, I go ahead and generate that, and you see it just gets rid of those fillets there. So a really useful tool. If I do it one more time, maybe for these interior fillets, I'm going to flood those blends, and let's do one more face delete there. And you can see now I have a much more simplified version of my flow domain. I have 3 different partitions, and now let's go ahead and give this a try. So if I come back to Workbench and I refresh my mesh, what you can see is I'm going to bring in the updated geometry. And the first thing that I want to check when I get into meshing is, do I actually have sweepable bodies? And an easy way to do that is if I right-click on the mesh folder, I come to the Show submenu and Sweepable Bodies. And what you can see is Workbench tells me, yeah, you know what, you did a good job. You do have sweepable bodies here. So you can go ahead and use a brick mesh method on them. So the first thing I'm going to do is insert a sweep method, and I'm going to scope it to this body on the left. Let me change the method from automatic to sweep. And maybe I'll control the divisions here. I only want 25 of them. Now, on the other end, I'm going to do, let's say, a multi-zone method. So I scope it to this body on the right-hand side. I say multi-zone. And I'm going to allow that to create a brick mesh using the multi-zone method on this side. In the middle, what I'll do is just insert a patch-conforming tetrahedral method. So you can see in this multi-body part, I have 3 different methods, and they're going to work. Perfectly well together. So they can be combined interchangeably. There's no issues as long as the sweepable sections are in fact sweepable. Now, if I want to record the order in which I mesh these, what I can do is use the worksheet. If I just right-click on Mesh and say Generate Mesh, it's going to go through the bodies in the order that Workbench decides. But if I want to have some control over that, what I can do is come up here to the worksheet, and if I click on the Start Recording, Workbench is going to keep track of the order in which I mesh these bodies. So first, I want to mesh this body on the left-hand side. So I'm going to select it. I can right-click in the graphics window and say Generate Mesh on Selected Bodies. So it's going to go through real quick, create that sweep mesh. As we can see, it gets a nice sweep mesh only on that body. And if we come back to the worksheet, what it's done is inserted a step in my mesh recording. So it says the name selection 10 is going to be meshed first. So if we take a look at that name selection, that corresponds to the body that I selected. Now if I want to go to this body next, I'll highlight that, generate the mesh there, and we're going to see the multi-zone method go through and mesh that body. And again, that gets added into my meshing sequence. finally, let's do the patch conforming in the middle. And we'll see that'll generate a nice uniform mesh using the patch conforming tetrahedral method on my more complicated region. So I have my meshing method recorded. I have a nice uniform mesh. I have hexes where I can get away with hexes, and I have teps in the more complicated regions. And I end up with about 215,000 elements. So quite a reduction in the mesh with just a little bit of geometry manipulation. And if I update, let's say, any of my dimensions in my CAD file, I have the mesh order recorded so that when I generate, it'll go right through in that specific sequence. Now, one last thing that I want to show you guys is that when I do this selective meshing, when I mesh the bodies in the order that I choose, the impact of that is that the bodies that I mesh first will influence the bodies that I mesh after it. So this was, on the left-hand side, the first body that I meshed. So if I go ahead and hide that, you can see on the tet, the body that I meshed with tet elements, on that interface, I have the influence of the previously generated mesh. So a really powerful way to control the mesh propagation across interfaces. Okay. With that said, hopefully I've showed you a couple of useful things here today. Just in summary, there are a number of different options for generating a mesh in Ansys Workbench. But recall that if we can fit hex elements where possible, that'll give us a much more efficient and controllable and high-fidelity mesh than if we just use a brute force method. So a little effort on the user end in the front is more powerful than just letting Workbench do everything for you. And the ease of use of Workbench makes generating high-fidelity meshes a very simple process.